Hey guys, welcome back to our second part for the coding of our digital thermometer. Apologize, it's been hectic. The holidays snuck up on me and I wasn't able to make any more videos. I got a lot of stuff that I had to do with my family and everything, so I apologize for that. More videos will be coming at you. Plus I saw some holiday stuff that I thought was kind of cool, like holiday electronics that we may look into how to make for maybe next Christmas. I was wanting to get a video out, kind of a Christmas video, but I didn't get a chance to. I had a lot to do, so apologize for that. But we're back, and we're back looking at the schematic again because I have a change. I'm going to post a comment on my previous part 1 video. I didn't even think about this, but since we're going to be using floating point numbers, floating point numbers take quite a bit of memory to deal with. I could have done this without using floating point numbers, but it gets a little complicated to do that, so we're just going to use floating point numbers. And what I did was, the first thing that you notice is different is I changed the processor. I went from the 676 that we had previously to the 886 is what I went with, because an 886 has 8192 memory, whereas the other one only has 1720, I think, or no, 1750. Only has 1750 memory. The 676 does. And so something like that, and it's not enough if you're going to be doing floating point numbers plus running the ADC plus running RS-232, which we're using a software RS-232, at least on that one. And so it just takes up too much memory. So switch processors. We're with the good old tried and true 886, and just wanted to point that out to everybody that we did change processors just because the code won't fit that I'm going to show you, that you can download then off of my channel page. And those of you that haven't visited my channel, I ask you to. That would be cool. There's a lot of helpful links on the right hand side. There's a bunch of links to different places that are very helpful, parts and manufacturers and things like that. And there's also the most important one is the project code link that has every project that we do in detail here is zipped up into a zip file and listed there that you can download freely from MediaFire. So that's for the code that I'm going to be posting up there and everything for you guys to download and play with. Will be for the 886 just because I'm using floating point numbers again to do this and make it a little simpler, so I have to use the bigger processor. Well, enough of that. What we're going to do is we're going to come back and look at our temperature sensor characteristic table. And what we're going to do for this is we need some way of correlating and being able to calculate what temperature that we're at. Now, you can do this a variety of ways. I find the easiest is to do a linear, or not really linear, but to do a regression method. Those of you that have done any type of statistics or plotting or whatever in that kind of mathematics, you can do regressions. You know, there's linear regression, there's quadratic regression, there's exponential regression, there's all those different techniques for doing it. Now, before I get all complicated and start explaining math to you guys, I'm going to show you this is actually really easy to do. What we're going to do is we're going to bring, if I can grab a hold of it, trusty dusty Microsoft Excel. Now, actually what I want to do is I want to show you guys that using Excel, you can have Excel do it for you. What I did was I copied and pasted these two columns. As you can see, column A is the temperatures, column B is the resistance values, and as you can see it's normalized around 25, like we explained before. There we go, normalized 10K. So, and this is all in K ohms. Now, if you remember what we're doing, so here, I'm going to get rid of this because now that we have this, we don't really need it. But if you remember, where is it? Here, let's do this so we can see it. If you remember, we got this type of a thing going on right here. We've got our 10K variable resistor or thermistor, and we've got another 10K right here. So if you remember that, our voltages, what I did was I just copied this column and put it over here, as you can see, and just put it over here because I'm going to use this to plot. But I calculated what voltage I'm going to see. So all it is a volt divider. I'm using 5-volt system. So I got 5 times and we're looking at the voltage across this resistor, so 5 times this one, 5 times 10, and it's all in K. This is all K, and this is K, so I dropped the K's. That's the reason it's just 10, because they're going to divide out anyway. So 10 divided by the sum of the two, and that's basic volt divider. And so that's going to be 10 plus our resistor value. Well, since it's this variable, we're going to say equal to this B, so B1. And then the next one is B2, and B3, and B4, and so on and so forth. And those of you that aren't savvy with Excel, once you type this in exactly like this, just copy, hit Control-C, and then drag all the way to the bottom and paste. And it'll paste it, and it'll go ahead and it'll calculate it for the subsequent, B5, 6, 7. It'll calculate it on down. Once you have that, we're going to do something kind of cool. If you select this way, like this, left to right and down, this is going to be, when I'm going to insert a plot here in a minute, and this is going to be your X values, and this will be your Y values. Excel automatically picks what's on the left as X, and whatever is on the right as Y. So any additional columns that are to the right of your first column, it will plot on the Y-axis, and this will be your X-axis. And so let me show you this. If you go up to Insert, Scatter, we want a line plot, okay, with smooth lines. That's what it says. So we're going to hit Plot. And there's our line. There's our curve. Okay, see that? So we've got a curve. Now I'm going to go ahead and maximize this and move this around. So there's our curve. Okay, now like I said, this is a scatter plot, so it's just data points and it just connects the dots. Okay, and see we're going from minus 40, all the way up to 125-ish, yeah, 125. Okay, now what we're going to do now is we're going to fit a line to this using a regression method. And then we're also going to have it tell us what equation it used to get us that line, because that is the equation we're going to use in our code. Now, you click on the data, just left click once on the data, right click, and then right click, and choose Add Trend Line. I think actually you don't even have to click on the data. No, you do. So left click on the data, then right click, and hit Add Trend Line. And this is going to bring it's going to shoot a line in, and it's going to bring up this format trend line. You can do logarithmic, polynomial, you can do power, but I think this one doesn't fit any of those. So you basically get these three. Then you can do moving average, which that gets complicated. Now the thing is, choosing logarithmic and choosing polynomial. If it's polynomial, it can become basically a quadratic, or it could be even a higher order. It could be a third, fourth, fifth order polynomial. Well, that starts getting really complicated to try to implement in a PIC microcontroller, because especially like an 886 or something, some little small 8-bit micro, you're going to have to go into a more robust processor to get to start doing polynomials. Same with logarithms. Start doing logarithmic differentiation and things like that. You're going to start getting into a higher end processor. Well, we want to stay simple for this tutorial. This is all pretty simple, basic stuff, and I don't plan on getting super exact. Now, if you are going for precision and you want a very, very, very precise thermometer, then I would suggest choosing polynomial, and then going with a higher end processor with a better ADC, and yada yada yada. I explained kind of that in my last video. And honestly, I probably wouldn't use just a thermistor. I'd probably use one of those discrete things, because it's temperature compensated, it's got noise rejection, it's got all kinds of stuff already built into the IC. I'd probably use one of those active thermistors instead of a passive thermistor like what we're using. So for us, linear is going to be fine. It's going to be easy. That's just regular old slope-intercept form. The y equals mx plus b. Super simple linear regression. Now, we chose that, and it plotted the line. Well, where's the equation? Well, if you come down here to the bottom, there's a deal that says Display Equation on Chart. How cool is that? And now we have the equation. How cool is that? Now, if we go back to our trend line, if we want to see how accurate this is, I don't know, those of you that may remember this, there's an r-squared value. Display that. And what the r-squared value will tell you now is it tells you how correlated the line is to the data. An r-squared value of 1 means perfect correlation. That means your line is exact. And then anything less than that, you're starting to deviate by a percentage. So we're within almost 5%, 4%-ish. We're within 4%. Okay? So that's pretty good. You know, at least for what we're doing, that's pretty good. So there's our equation. That's what we're going to use, is this 30.759 times X, in this case, is our voltage, so whatever our voltage reading coming out of the ADC, and then minus 45.674. And that should give us pretty close to temperature, to what temperature it is. So, now knowing that out of the way, and we know what we're doing here, we've hooked it all up, supposedly. Now we can move to our code. So here's our coding section. And for those of you that this may look a little blurry or whatnot, if you check your video settings when you're watching this on YouTube, excuse me, check your video settings and set it to a higher resolution. So set it to like whatever it is, like 720p or something like that, to give it a higher resolution in the actual video. And then also, like I said, this code will be posted. You can download it and follow along if you have a slower connection and can't run the higher resolutions. You can always follow along listening to what I'm doing with that. Okay, so we have our include, and just like my ADC one that I have, I'm not really going to run through this piece by piece, because if you want to see how to set up an ADC and you want to see how to set up RS-232, go to my channel, check out. I think I even have playlists over on the right hand side. There's playlists for those. If it's not in the ones shown on my channel, there should be at the bottom of that, there should be a deal that says show all playlists, and then it should be in there somewhere. It should be the ADC one and the RS-232 playlist. If not, send me a PM. I'll gladly send you where to go, but you can always sift through my videos. Okay, so we set up our ADC stuff, yada yada yada. We're going to declare some variables. We're going to declare a long value, and make sure it's long if you're using the 10-bit. If you're setting up your ADC to use 10-bit, make sure you use a long value. I think I may not mention this in my ADC tutorial. I'm going to have to go back and review it, and I may put notes in it about that. But make sure you use a long, because if you're 10-bit, well, 10 bits is 1024, right? Is 1024. 2 to the 10th is 1024. So basically you're going to get a digital representation that will be an integer value anywhere from 0 to 1024. Well, if you put it in just a normal int, and in CCS, which is what we're using the CCSC compiler, just the int designator defaults to an 8-bit integer. Well, you only get 256. It'll only go up to 256, and then that's it. So you're going to overflow your variable, and so you'll get weird, wacky answers. So make sure and use a long, because a long in CCS lingo is considered a 16-bit integer. It's an int 16. So then you get 16-bit. Well, then you got what, 32,768. So you got a lot larger number that you can store in your variable. So make sure and use long. And then yada yada yada. We're going to get some float voltage and degrees is what I called it, so I can separate them out. And then on down to, we're going to display digital thermometer, yada yada yada, and then we're going to read our ADC into value. Then once we have that, we have to do the conversion from the digital representation, because like I said, it's going to be an integer value, okay? And so it's going to be just a number. We have to convert that back. Well, if you're using, we'll do this. Let's grab the calculator here. If you have 5 volts, okay, and you cut that up into 1024 different pieces, you're going to, oh crud, I have this on programming. Okay. Let's try this again. 5 divided by 1024. You're going to get about 4.88 millivolts, per number, okay? So for every digit, that's about 5 millivolts. So what I did is notice this number and that number look a lot alike. It's because whatever value you have, to get the voltage until you get the voltage that that's representing, you have to multiply your ADC value read by the ADC by 0.00488, 28125 or something like that, However you want to round that off. I just went ahead and put in a whole bunch of numbers. But you have to multiply it by that to get your actual voltage value that it's seeing, or at least the ADC's interpretation of the voltage. Now that we have the voltage, let's see, I'm going to go back to grab our little deal here, see if I can shrink it. There we go. Okay. Now I'm going to grab our equation. Now look very closely. Let's see if I can get this like huge so you can see it. Okay. If you notice, right here, I've got, to get my degrees, I've got 30.759 times our voltage value, which X was our voltage, and then I'm subtracting 45.674 off. Okay, so there's our equation. There's our equation that finds, right there. That's our equation that finds, right here. That's our equation that finds our temperature. And now all we got to do is display it. Real easy. What we're going to do is we're going to do 0.2f, which gives us 2 decimal places after the decimal on the float, and then f. And then I did this %c thing because I'm going to put the degree symbol in. So that's what this DSYM, it means degree symbol. It's the little circle, that little tiny circle that you get. In fact, I can probably show it to you right here. Or wait, no. There we go. That little degree symbol. So I can do degree C like that. Like that. That degree symbol is A7, is what that is in hexadecimal. So I just created a character called DSYM equals, and then the symbol A7, and then all I'm doing is saying %C, and then the letter C. So I get a degree, and then I get C. And then a new line in return, carriage return. And then I put my variables in for the float. I put degrees. For the little degree symbol, I put the D symbol variable. Then what I'm doing here is I'm just waiting 3 seconds before I display the next one. So I'm taking a temperature measurement every 3 seconds is what I'm doing here by having it delay 1,000 milliseconds, 3 different times. And guys, that's pretty much all there is to it. Pretty simple, pretty straightforward. Just using the volt divider to your advantage and using a little math and a little bit of programming, and voila. I will go ahead and create a video, a functional demo video of this actually working. I actually have built this up and tested this code. This code is good. It does work. I won't have any changes to it come demo video. And I'll probably post the demo video fairly soon, if not right after this one. And yeah, stay tuned. More upcoming stuff on the way. More ARM stuff to play with. More just miscellaneous things I can think of to play with. I got some kind of cool stuff with some LEDs. I found a great place to buy LEDs for fairly cheap, and you get 100 quantities of them. So we may do some pretty cool stuff with LEDs and play around with light. Excuse me. I've been seeing a lot of cool stuff on YouTube. You guys have been building some really neat stuff. Really great stuff I've been seeing out on YouTube, and so some stuff I've been seeing that I'm not seeing exactly how they're doing it, so I may take some of that and do it myself and then post it for you guys. So if you guys ever wondered how some of this stuff goes together, you'll be able to see it. So stay tuned, keep the code rolling, and take care, guys. Remember, always have fun, because that's what it's all about, having fun. Talk to you later, guys.